We're going to move on to the next part in our notes on complex numbers, and that's factorising polynomials over the set of complex numbers. Now, you've done factorising of polynomials before, but that's over the set of real numbers. Okay, so we're now looking at factorising it over the set of complex numbers and then being able to solve equations. Now, being able to do that requires us to complete the square. Okay, in this first example, we've got a quadratic, and to factorise quadratics in complex numbers, we need to be able to complete the square. So I just want to remind you how to complete the square. You'll notice that in this quadratic we have our leading term, which is the power of 2, our next term, which is our z to the power of 1, and our constant term. Now, when we're completing the square, what we're aiming to do is to get our quadratic as a perfect square. So, for example, let's look at a different one altogether. If we were to expand, say, just very simply, x plus y squared, okay, so this is what I mean by perfect square. If we were to expand that, then we're going to get x squared plus 2xy plus y squared. Okay, our first term is squared, our last term is squared, and our middle term is twice the product of our two middle terms in the brackets. Okay, so when we're completing the square, we're aiming to get it in this form, because we know that if it's like this, then we can factorise that to get x plus y squared. So what we need to do is, if we were to have something like x squared plus 4x. Now, the rule for completing the square is to add the square of half the coefficient of x. So the coefficient of x is 4. We need to add the square of half of that. Okay, half of that is 2, and we're going to square that. Now, if we're going to add that, we're changing our expressions, so we also need to subtract it as well. So what we have here then, this part here, is what's going to factorise to our perfect square. And so that becomes x plus 2 squared. Just like we had here, we've got our x squared here and our y squared. Alright, so inside the brackets we have x plus y. In this case we have x plus 2. Okay, so that's what that expands to. And so to complete the square on that, what we had to start with is x plus 2 all squared. We still have this part at the end, which is going to be minus 4. Okay, what we would then do is go that step further, because we have our what we call a difference of 2 squares. That's going to further factorise to x plus 2 minus 2 x plus 2 plus 2. Okay, so that's our difference of 2 squares, which is factorised, and of course this one here is fairly straightforward. It's going to then become x plus 2 minus 2 is just x, and x plus 2 plus 2 is x plus 4. Okay, or x times x plus 4. Now you'll notice that that is the same result as what we would have gotten had we just done that as a simple way. We take out a common factor of x and we're left with x plus 4. Okay, completing the square is, in this case, a much longer way of doing it. In some cases it's the only way. Okay? Now, what we're going to do is apply that to our quadratic here, where it's essential that we use completing the square. So you'll notice that we've got as our starting point, z squared plus 4z plus 13. And what we want to do then, just ignoring our 13 for the moment, we need to add the square of half the coefficient of z. And so in this case it's plus 2 squared, so it's just like in this example we did here. And so factorising that gives us z plus 2 all squared. But we've also had to subtract 2 squared, okay, to keep everything in balance, to keep everything the same. If we're adding 2 squared, we need to also subtract 2 squared, otherwise we're changing our expression. So minus 2 squared is minus 4, plus 13 is plus 9. Now you'll notice that what we've got here, it's not a difference of 2 squares, it's a sum of 2 squares. And so you can't factorise like we did here because it was minus. So what we're going to do is change our plus 9 to incorporate a complex number or imaginary number. Okay, so plus 9 is going to be the same as minus 9 times I squared, because you know that I squared is equal to negative 1, and negative 1 times negative 9 will be positive 9. So we're just rewriting our plus 9 to be minus 9i squared, which is equivalent. Okay, now 9i squared we could write as 3i in brackets squared. Now we have a difference of 2 squares, okay, which we can factorise to z plus 2 from our first square minus 3i from our second square. Okay, and then z plus 2 plus 3i, just like we did with this one, minus 2 plus 2 minus 3i plus 3i. Okay, so I hope that's clear. Okay, and this is it fully factorised. So what we have, what would be not factorisable normally, okay, when we think about real numbers, in the complex set, we can factorise it. We get 2 complex numbers as our 2 factors. Okay, let's have a look at another example. This one is a little bit more complicated because our coefficient of z is not a real number, but it's a complex number. Okay, so let's have a look and work through that one as well. So we have 4z squared plus 8 minus 4i times z plus 3 minus 4i. So our coefficient of z is a complex number and our constant term is a complex number. And so what we want to do, in order to complete the square, we need to have our coefficient of, or our leading coefficient, needs to be 1. So we're taking out 4 as a common factor so that we've got inside these brackets a leading coefficient of 1. Now in order to take 4 out as a common factor, we need to change our other 2 numerical parts. So we've got 8 minus 4i over 4, and our constant term is now 3 minus 4i over 4. And that simplifies here. Okay, so we can take out a common factor of 4, and when we cancel with that 4, we're left with 2 minus I. This one here remains the same. And then we can go ahead and complete the square. So we need to add the square of half this coefficient. Okay, so 2 minus I over 2. That's half of it. So we just have to leave it like that. And we're going to square that. Now because we're adding that, we also need to subtract it to keep everything equal and the same. And then we've got our constant term on the end. So the next step is these first 3 terms then constitute our perfect square, and we can factorise that to z plus 2 minus I over 2 all squared. And then this one here, for the remaining terms, 2 minus I over 2 squared expands to 4 minus 4i over I squared over 4. And we can simplify that. Plus I squared becomes minus 1, so 4 minus 1 is 3. And so we're left with 3 minus 4i over 4. Okay, now this here is being subtracted, and so we've got minus 3 minus 4 over 4 plus our constant term, which is the same. So these two terms here are going to cancel each other out. And so we're left with just our perfect square. Okay? Z plus 2 minus I over 2. And to simplify that, okay, we can break this up into two fractions, 2 over 2, which is 1, and minus I over 2, which is minus 1 over 2 I. And then what we're doing to go from here to here is to bring the 4 inside. Now how can we do that? Well, 4 is the same as 2 squared. And so we're taking our 2 inside. Okay, so it becomes 2 times Z plus 2 minus I. Okay, and that just is a neater form rather than leaving it like that. Although even if you left it like that, it's not wrong. This is just a nicer way of presenting it. Okay.